Okay, let's now look at another example. We've seen what happens to the supremum when we translate a set. Now what happens if we perform a dilation? So we multiply the set by a number c. So we have the following property. So property let c be greater than or equal to 0, and let a be a bounded, or maybe a subset of R, be bounded above. Okay, so let A be a set that is bounded above, and let C be any number greater than or equal to 0. We by the least upper bound property of R we know that A has a supremum let us denote by S the supremum of A, of the set A. We also define C times A to be the set of numbers of the form C times A, where A belongs to the set A. So it's completely analogous to the two translations. We're now multiplying every element in A by the constant C, and that's going to be the set C times the set A. So this is a definition. So what is a property? What do you think? What do you think happens to the supremum? If you think that this is equal to C times S, then you're right. So if we forget about the C in here, just look at the set A and A, that's the supremum. The supremum of that set would just be A. So what happens when we multiply everything by A? Then the supremum will also be multiplied by A, because for the same reason we saw above, we'll be able to perform the same kind of operations that we did before when we move things from one side to the other, in order to reduce this statement of that C times S is the supremum of the new set C times A. We're going to be able to write it in an equivalent way, or to reduce the proof of that to just the property we already know that S satisfied by virtue of being the supremum of the set A. So if you said that this was the case, then you have a very good intuition. That's actually true. So what we need to show again, so we need this is the same table that we had before. So we want to show two things. We want to show that given, so the first one is this is going to be this is what we're going to prove first. So that's our first step. But it's a property one. So given R in CA, we want to show that R is going to be bounded from above by CS, because that's what we're claiming. So this is just showing that CS is an upper bound. The second statement is given an upper bound B, upper bound for CA, we want to show then that B is greater than or equal to C times S. And what do we know? So what we know is that 1, given A in A is less than or equal to S, because S is an upper bound. And the second thing we know is that given K an upper bound, for A, S is less than or equal to K. Okay, so when showing 1, we're going to try to write it in a way that looks like in a way that looks like this statement over here, statement 1 of what we know. So we'll be able to conclude that, right? And the same thing for 2. We're going to write it in a way that resembles 2 from the part that we do know. Okay, so where's for the proof? So first step is just showing 1 from the left hand side. So given R and CA is where we actually use the structure of A, we know that R is equal to C times A for some A in A. We know that. I mean, that's the definition of the set CA. Right, that's the definition of the set CA. So all the elements of the form C times some element in A. So this is the definition of the set CA. So if R belongs to that set, it can be written in this form. C times an element in A. Okay, so we know that R is going to be equal to that CA. Remember they want to show that R is bounded from above by CS? Well, now we use what we know, which is this statement here. We know that A is less than or equal to S. Right, so from some A in A. So we pick here what we have, so we know that A is less than or equal to S. And how do we make C appear here and CS appear here? We use the fact that C is non-negative to deduce this. Remember that C is greater than or equal to 0, so we don't we don't mess up the inequality, so the inequality remains in the same direction, pointing in the same direction. If A is less than S, less than or equal to S, then CA will be less than or equal to CS, because C is non-negative. So it preserves the direction of the inequality, meaning that this sign here points in the same direction as this one. Okay, and so that's how we use the first property. And so we've shown here what we wanted to show was that CA. Remember, the CA is just R. So R is less than or equal to CS, and this is what we wanted to show. That was the first step. This is what it says over here, and this is what we've established. So what about 2, the second step? So the second step is showing 2. Given B, which is an upper bound for CA, we want to show that CS is less than or equal to B, and we will need to use the statement 2 that we know, right? The statement 2 that we know. Okay, so let's give it a try. Remember that we want to, just like we used the statement 1 here, we're going to use the statement 2, what we know. Second step, okay, so we have an upper bound. So B, so let B be an upper bound for CA. This means what? If we pick that if R belongs to, it's an arbitrary R, so for all R in CA, R is going to be less than or equal to B. But this is the same as saying that for all A in A, C times A is less than or equal to B. These statements are the same. Why? Because every R in CA is of the form C times A for some A in A. So you go over all the values of A in A, you can obtain all the R's in CA by simply multiplying those elements A in A by C. So we know that C times A is less than or equal to B. Right, so here there are two possibilities. So one is that C is the number 0. And if C is the number 0, then B must be greater than or equal to 0, in which case B, of course, is greater than or equal to C times S, which is 0 because C is equal to 0. If C is positive, on the other hand, so if C is positive, I mean, we already said what happened when C was equal to 0. The case C equals 0 is left as an exercise. But we just said how to do it. But if C is greater than 0, then we can divide by it. Remember, the C is positive, so we're going to preserve the same inequality. And why do we divide by C? Because if we just want to isolate the A that belongs to A, to use this statement here that we know, K is an upper bound, then K is greater than or equal to S. What does this mean? If K is an upper bound for A, it means this is if and only if for all A in A, we have that K or A is less than or equal to K. This is the statement that K is an upper bound. For all A in A lies below or is equal to K. And this is what we said. I mean, for all A in A is less than or equal to B over C. So this means that B over C is an upper bound for A. So this is our K. And if we know that we have a K, which is an upper bound for A, then K must be greater than or equal to S. And here's where we're using what we know. So K must be greater than or equal to S. Okay? So if it's an upper bound for A, so therefore, we must have that S must be less than or equal to B over C, which is equivalent again because C is positive. In the case where C is positive, remember that the C equals 0 is trivial, so it's left to you. C times S is less than or equal to B. Okay, and this is exactly what we wanted to show. This was the second property that we wanted to show here. CES is going to be less than or equal to B. Go over this proof very thoroughly because I may ask something like this in the exam. So this is a very crucial example on how to show things using the supremum. So this is the kind of thing, I mean, besides, you know, the problem sessions and the homework problems, although for this particular exam, I'm not gonna be asking anything anything really related to the homework problems because these are, I mean, as complicated as the homework problems because these are just a one-time thing that you need to learn. But it really has no bearing in what we're gonna be doing next. So something that needed to be done. Okay, but this is more up the alley of what we will be seeing in the next couple of weeks. So try to go over this example again. If you have any questions, send me an email. Of course, we won't have office hours before the exam, which will be during class time. But yeah, so it's during class time. Yeah, so and that happens before Friday. So, but what we can do is to meet if you want. So if you want to make an appointment on Wednesday, I'll be available basically all day. So remember to email me or to send me a message through Canvas. Again, if you want to schedule an appointment, the idea is that you don't miss any opportunities to ask for help. So I'll be connected and we'll be seeing what you guys have to say or to ask before the exam. Okay, but that's the information about the exam. I'm gonna post something related to the exam. You need responders and lockdown browser and all those things. I mean, they are described in the syllabus. If you have any further questions, but for now, we need to continue with the material. And the next thing that they wanted to talk about is a very important property. Something I mentioned last week is a very important characterization of the supremum. Okay, so this is a lemma in the book. I don't remember exactly the number, but this is the following property. So let me just complete it then next. Or you can tell me it's 1 point something. The lemma says the following: So if S is in R, so it's a real number, it is an upper bound for a set A, then S is the supremum of A if and only if given any epsilon greater than 0, there exists an A in A such that A is bigger. So S minus epsilon is smaller than A. So A is bigger than S minus epsilon. And so this is a property, and this is what we're going to show in the next video. It's already 21 minutes. But just visually, so the idea is this. So if you have, this is the way to think about it. So you have a set, I'm going to draw it vertically. So you have a set A. This is your set A. If you have an upper bound B, this cannot be the supremum if there is a gap between the set A and B. Because whenever there is a gap between A and between the set A and the upper bound and number A, maybe poor choice of letters. But then you can go a little bit lower and that will still be an upper bound. So B could not be the least upper bound. So the supremum must be something that is almost touching, or it is touching the set A. And so whenever I lower this a little bit by some epsilon, there will be some elements here in the set A. There must be some elements here in the set A that are bigger than that S minus this epsilon. And that's the idea. So an upper bound, the upper bound, the least upper bound, cannot be detached from the set A. Okay? And that's what we'll do in the next video.